Law of mass action, the trick that I used where mass that goes in is equal to the mass coming out, does work. However, there's another little wrinkle that has to be considered, and that's called a limiting reactant, all right? And in a given reaction, sometimes you don't have enough of one chemical to react with all of the other one. Notice they're using reagent. A reactant, technically, is a chemical to the left of the arrow in a balanced reaction. A reagent is a chemical that you add from a lab to make something happen. For our purposes, reactant and reagent are the same thing. You will see them both. They're technically a little different, but it's pretty cheesy, so just ignore it. Think of reactant as reagent. Likewise, you'll hear limiting reactant and sometimes limiting reagent too. Don't let that bum you out. For example, if you have a room of 20 really thirsty students and you have 2 bottles of water, all right, you are going to have the bottles of water limit how many students can get water, all right, because assuming it's 1 bottle per person, you could only give them 2 people the bottle. You'd have 18 people that didn't have water. So in that case, water would be the limiting reactant, limiting reagent. On the other hand, if you had the same 20 students that were thirsty and you had, let's say, 50 bottles of water, well, now you have fewer thirsty students than you have water. So the thirsty students would be the limiting reactant, limiting reagent in those kind of situations. This is a very real thing in chemistry. We're going to see later on in Chem 223 that there are some chemistry reasons why you might want to have a limiting reactant, and we'll talk about those in that class later on. But for right now, just realize this is something that happens and there are ways to take care of it. But first, here's a silly example. Now, this is an example of you coming back with your friends maybe after a concert or whatever, and you're all really hungry. Now, I am a vegetarian, so I'm going to assume that the hamburgers are garden burgers, but you can use meat burgers or whatever you want in this example. It's no problem. I am not a vegan, so having a cheese would be okay, at least in limited quantities. But if you are vegan, let's assume it's a vegan cheese, etc., etc. If you're gluten-free, then they're gluten-free buns, etc., etc. Anyway, digressing once again. You come back with your friends. You're really hungry. You look in the fridge, and you haven't been shopping for a while. And here's what you've got. You've got 3 burger patties. You've got 6 half a dozen hamburger buns, and you've got 12 or a dozen slices of cheese. And you and your friends really, really, really want to make, let's call it the ultimate cheeseburger. And the ultimate cheeseburger has 1 patty, 2 slices of cheese, and 3 buns. Okay? Well, you can probably see right away that because you only have 3 of the patties, you're only going to make 3 of these ultimate cheeseburgers. But let's say you hadn't looked yet in the freezer and you have 6 buns. And so you think, score, I can make 6 of these ultimate cheeseburgers. Awesome. But then you see, I've only got, 3 patties, so I can't do it. So the patties here are limiting the product. The patties are the limiting reactants. The hamburger buns are the excess reactants. Like you can see, there's stuff left over down here. You got buns left over, no problem. And you could do the same kind of argument with the slices of cheese. If you need 2 slices of cheese per ultimate cheeseburger and you have 12, in theory, you could make 6 ultimate cheeseburgers. But no, once again, hamburger patties limiting you make. So you have 6 slices of cheese left over. Cheese also is an excess reactant. So notice here the importance in this. The limiting reactant, the hamburger, really limited how much product we could make, all right? And the other pieces are excess reactant. If you just looked at those, you'd think, oh yeah, I could make 6 of these ultimate cheeseburgers. No, you can't, because again, the limiting reactant stops. So in chemistry world, you really want to know what the limiting reactant is. This is a not so exciting version of the limiting reactant in terms of chemistry. I kind of like the other one, makes me hungry, whatever. Anyway, this is the reaction between nitrogen monoxide, NO, and O2 oxygen to make nitrogen dioxide. And if you look at the little boxes, it's like before and after. And if you look here, you have 1 to 3 O2 molecules, and the nitrogen is a blue, so you can see the blue-red combination is NO. That's 1, 2, 3, 4 NOs. So if you look at just those numbers, 4 NO and 3 O2, well, NO is a lot more of them. There's 4 versus 3, so the O2 must be excess, etc., etc. However, in what we're making here, NO2, when you use the balanced reaction, it's 2 NOs are needed for 1 O2 to make 2 NO2s. And if you look on the product side, we have 1 NO2 right there, and a second one, and a third one, and a fourth one. There is 1 O2 left over, but you'll see that there's no NO left over, all right? If there's no reactant left at the end, then that means you've got a limiting reactant. NO is your limiting reactant. There's nothing left on the product side. If there is a reactant left, i.e. O2, that means it's an excess reactant, all right? So even though there were 4 NOs and only 3 O2s, because of that 2-to-1 ratio, we did use up all the NO, and we have O2 left over. So O2 is left at the end. That makes it an excess reactant, and the other reactant, the part that's gone, in this case NO, that's going to be the limiting reactant.
For this demonstration, we put 3 different amounts of zinc into the same amount of hydrochloric acid. At the end of the reaction, there is still some zinc remaining in the flask on the left. The reaction on the right did not generate as much gas because there was an insufficient amount of zinc. In the center reaction, the balloon inflated fully and all the zinc was consumed.
In this reaction, which I think is pretty clever, each of those little Erlenmeyer flasks with a balloon on them, each of them has 0.100 moles of hydrochloric acid, which is HCl, and it's HCl-AQ. This is the first time we've run into it. AQ means aqueous, which means dissolved in water. So the HCl is dissolved in water is what that means. And the balanced reaction, which will be helpful to us, zinc metal, or zinc as a solid, is reacting with 2 hydrochloric acids to make zinc chloride, ZnCl2, plus H2 hydrogen gas. And again, note, hydrogen's one of the diatomics, have no fear of ice clear brew. So that's why it's H2. Zinc is not a diatomic, so it's listed by itself. Now, the size of the balloon is indicative of how much gas is made. So you'll see on the right-hand side, the balloon is pretty small, but the middle and the left balloons are both about the same volume, all right? You'll also see, if you look at the bottom, that right about right there, so whoops, a little bit there. There we go. Sorry, kind of sloppy. There's a little bit of zinc left in that one, okay? And there isn't any solid zinc left over in the other 2. So in the center Erlenmeyer flask, you have the exact amount of zinc needed to react with 0.100 moles of HCl. So in the middle, you have no zinc left and you have no HCl left. It's all gone. On the left side, the part I circled there, and circled pretty sloppily, by the way, we do have zinc left over. Zinc is the excess reactant, and the HCl all reacted to make the H2 gas. Notice how the balloons are the same size. In the middle, all the HCl was used up and all the zinc as well, and the balloon was that big. And the left side, all the HCl was used up as well. Balloon was the same size. On the far right, though, now we have not enough zinc, all right, to react with all the HCl. Like the balloon wasn't as big. We used up all the zinc that was there because HCl really wants to go, but we didn't have enough zinc to react with the HCl, so it's smaller. So this is the effect of the limiting reactant, and you can make any reactant a limiting reactant if you know your quantities right. So on the left-hand side, we had too much zinc. On the right-hand side, we had not enough zinc or more HCl, whichever way you want to look at it. The middle part is where we had just enough HCl to react with the zinc. So everything was used up and you're good to go. Mathematically, you can use these kind of numbers to figure out those quantities. Now, the ratio here is 1 mole of zinc to 2 moles of HCl. So here's the mass of zinc that were used in the 3 containers. 7.00 grams on the left, 3.27 grams in the middle, 1.31 grams on the right. Let's turn those into moles. Zinc is about 65 grams per mole on the periodic table, so 7 divided by the molar mass of zinc, 0.107 moles of HCl. Notice in the center, that comes out to be 0.050, and on the right, 0.020 was how many moles of zinc we had. Now, the reason the middle part was balanced is that all of them had 0.100 moles of HCl. And again, 2 HCl's per 1 zinc, you can see that the moles of HCl are twice as big as the zinc in the middle. But on the left side, the moles are almost equal, all right? And on the right side, instead of a 2-to-1 ratio, you have more like a 5-to-1 ratio. The HCl really outnumbers the zinc on the right side. So you can figure out ratios and stuff like that, which is cool. If everything is balanced, you'll have 0.0500 moles of zinc. And that's, again, what we have in the middle. So that's the balanced amount, all right? But on the left-hand side, we had an incredible difference. We had a lot more zinc than we had HCl. So that's why the HCl on the left-hand side is the limiting reactant. All right. Remember in the picture, there was zinc left over in that one, and the balloon was totally filled, which means we used all our HCl. On the other hand, on the right side, there was no zinc left over, and the balloon wasn't filled all the way. So that means we didn't use all the HCl we had. The zinc was the limiting reactant in that case. So again, it's really important as a chemist to know which is limiting and which is the excess reactant, and you can go from there. Ammonia, prepared by the reaction, N2 plus 3H2 going to 2NH3, similar to what we looked at earlier. So here we're mixing 10 moles of nitrogen with 25 moles of hydrogen, and the limiting reactant is, and there's basically these possibilities. Stoichiometrically balanced just means that you have exactly the right amount of nitrogen for the right amount of hydrogen, and that does happen sometimes. That was the middle example in the last thing we looked at. But then you also have nitrogen, you have ammonia, and you have hydrogen. So automatically, all right, is that if you're looking for a limiting reactant, it cannot be the product. So answer C is out. That's a product. It's not a reactant. You could have N2, you could have H2, and you could have ammonia. Now, if you look at just the raw numbers, 10 moles of N2 and 25 moles of H2, it looks like H2 is a lot bigger number than 10, and it is. So it feels like you should say, well, H2 is in excess and nitrogen's the limiting reactant because it's smaller. But remember, there's another thing we have to think about. 1 nitrogen needs 3 hydrogens. So you need 3 times the hydrogen to react with nitrogen. And you're probably saying, aha, because if we have 10 moles of nitrogen, that means we would need 30 moles of hydrogen. And we only have 25. We have less hydrogen than we need to react with that much nitrogen. So even though the number is bigger, hydrogen is the limiting reactant. Now, mathematically, what you can do is you can figure out then these kind of things. And here's a way to do it. I'm turning the moles of the reactant, either N2 or H2, into moles of the product, NH3. And this is what we're going to do here in a little bit. So notice for the first one, 3 moles of H2 were needed for 2 moles of ammonia. And that's where we multiply the 25 by, and we get the 16.7 moles of ammonia. If you do that for the nitrogen, 10 moles of nitrogen, it's a 2-to-1 ratio. Notice the first number is the same, but the second one changes because, again, 1 N2 for every 3 H2. Anyway, you end up with 20 moles of NH3. the smaller product is going to be the answer. And 16.7 is smaller than 20. And because 16.7 came from the H2, that means the H2 here is the limiting reactant. We're going to see that 16.7 is the theoretical yield of ammonia in this example. But that's not important right now. What is important is just recognizing what the limiting reactant is. Here's a reaction we're going to look at between aluminum and chlorine, making an Al2Cl6. This is an aluminum chloride dimer. It's a twisted metal. Aluminum is just like boron we saw earlier. Anyway, that's neither here nor there. The question is, we're mixing 5.40 grams of aluminum with 8.10 grams of chlorine, and it says how many grams of aluminum chloride can it make? And it might be tempting to just add 5.40 plus 8.10, and whatever that answer is, that would be your answer for Al2Cl6. And if the reactants are stoichiometrically balanced, which means the correct mole ratio, that process would work. But more often than not, if you see two reactant gram amounts, this is probably going to be a limiting reactant problem. And what that means here is we have too much aluminum for the chlorine that's present, or we have too much chlorine for the aluminum that's present. And before we figure out how many grams of the product can be made, we've got to figure out what the limiting reactant is. Now, I'm going to show you a couple different ways to do this. And the first way is the classic way where you use ratios. If you're a ratio person, this way is a little less work than the other way. On the other hand, if you're more of a plug and chug kind of person, you're going to like the second one better because there's lots of uses for it. Also, you might have seen these kind of problems done a different way in other classes, and you don't have to do it the way that I'm doing it here. So just realize there's some flexibility on how you're going to answer these questions. If you're going to do this the ratio way, all right, you want to compare the mole ratio of reactants to the theoretical mole ratio. Now, the theoretical mole ratio is just the stoichiometric ratio of the pieces in there, and that 2 ALs to 3 Cl2s is going to be really important. If you're going to have a theoretical mole ratio or a stoichiometric ratio of possibilities, 3 moles of Cl2 would be needed for every 2 moles of Al. And if those mole ratios are 3/2 or 1.5, then you're going to be good to go. And adding up those gram reactants will give you the answer gram of products, which is really cool. But like I said, more often than not, that's not the case. It is not the case on this problem. If your mole ratio of chlorine to aluminum is larger than 3/2, all right, like let's say the ratio, you calculate the moles of Cl2 and the moles of Al, and it comes out to be like 4, all right, a number bigger than 1.5, then what that means is you have too much chlorine. You don't have enough aluminum to use up the chlorine. And if you don't have enough aluminum, that means your limiting reactant is aluminum. So if the ratio is larger than 3/2 in this case, that means too much chlorine, not enough aluminum. Not enough aluminum means aluminum is limiting. On the other hand, if your ratio is less than 3/2, like let's say it's 0.75 or 1.1 or something like that, all right, then what that means, it's the opposite. Then you don't have enough chlorine to react with all aluminum. Chlorine is stopping the production of the product Al2Cl6. So if the ratio is less than 3/2, that means in this case that your chlorine is the limiting reactant. So notice that the ratio method, it really depends on how you set it up. In this case, it was chlorine over aluminum. And if the ratio came out to be less than the stoichiometric ratio, then the limiting reactant was the top part. But if the ratio is larger than the 3/2 in this case, then it's the bottom part that's going to be the limiting reactant. Let's go back. Let's do some math here. 5.40 grams of aluminum and 8.10 grams of chlorine. How much Al2Cl6 can we make? All right, so first we've got to have things in moles. That's going to be that mole ratio. So I took the grams of aluminum, I turned them into moles of aluminum. I took the grams of chlorine, turned them into moles of chlorine. Remember, chlorine's a diatomic, so 2 times the mass of chlorine. I only used 3 sig figs because that's all the 3 sig figs we had. You could use more than that if you'd want to. That's not a problem. There are the moles. And now with this ratio method, we're going to find moles of chlorine over moles of aluminum. If you do that, the actual numbers we just calculated, moles of chlorine over moles of aluminum, 0.570. It's a value which is less than 3 over 2. If it was 3/2 or 1.5, then that would be an exact ratio, and our chlorine and aluminum would be balanced. So, like I told you earlier, this is not a relationship where the reactants are balanced. We do not have enough of one of them. And in this case, the limiting reactant is going to be the chlorine. Now remember, if the chlorine was bigger amount, then 0.570 would get larger, all right? But here, the ratio is much less than 3 over halves. That means the limiting reactant is going to be the chlorine, the part that's on top. And remember, if this way is weird to you, I've got another way coming up, which I find a little easier, although it is more work. Once you know what the limiting reactant is, you want to base all of your calculations on the chlorine, because just like we saw the number of burger patties limited how many of those ultimate cheeseburgers you can make, in this chemical reaction, it's the chlorine which is going to determine how much Al2Cl6 you can actually make. So essentially what we're going to do is go grams to moles to moles to grams, starting with chlorine. And we already did the grams to moles part. We'll then use a 1/3 stoichiometric ratio to go to moles of Al2Cl6. And finally, the molar mass Al2Cl6 will turn moles into grams. So we calculated earlier 0.114 moles of chlorine. We're going to use the relationship of 1/3. That means 3 moles of chlorine on the bottom, 1 mole Al2Cl6 on the top. And we're doing that because we want the moles chlorine out of here. That 0.0380, that's the moles of the Al2Cl6 that can be made. And then you can take that moles of Al2Cl6 and multiply it by the molar mass, 266.4 grams per mole. We should be able to make 10.1 grams Al2Cl6. That's the theoretical yield of Al2Cl6 in this reaction. A lot of people can get through the ratio method with no problem, and that's fantastic. But I am going to show you an alternative method, which I find more straightforward, even though it is a little bit of work. But you're welcome to go back and pause and look at this example and stuff to make sure you got it going on. As I've been teaching chemistry, I used to use the ratio method all the time, but I have found and stuff another way to do these kind of problems. And it looks kind of weird, all right? But it is very straightforward. And once you see how it works, it's pretty cool. And I find it cool. This alternative method is also good because it will show you instantly not only what the limiting reactant is, but it will also show you what the theoretical yield was. And it'll then, by default, tell you which one is excess reactants and stuff like that. So I am using this way more personally than I do the ratio method. In a ratio method, you can flip reactants around and sometimes it gets confusing, but this way, very straightforward. And what we're going to do on this one is we're going to start with grams and go all the way to grams of product. One big sweep. And we're going to do it for both the Al and the Cl2. So there's going to be a lot of math here coming up, but we're going to look at those last numbers, the grams of Al2Cl6, to get our reward. So here's some stuff and no problem. So let's talk about it. In this problem, you started with 8.10 grams of chlorine and 5.40 grams of aluminum. Now, in both the top and the bottom examples here, we're just going grams to moles to moles to grams. And let's look at the difference here. The first part is going grams to moles for what you're starting with. So aluminum, 27 grams, chlorine, about 70.9 grams. The next part is the moles of what you're starting with to moles of product. So it's 2 to 1 for the lower one because it's 2 moles of aluminum for 1 mole Al2Cl6. On the other hand, for chlorine, it's 3 on the bottom and 1 on the top. All right, because there's 3 moles of chlorine chlorine for 1 mole of product. Then the last step is the same on both. It's just the molar mass of what you're looking for. That's the same number. You're turning moles into grams. The last part is what I find really cool about this. Notice here you get 10.1 grams from the chlorine, because this number again came from the Cl2, and 26.6 grams of product from the aluminum. Now only one of those numbers can be right, all right? And guess what? It's the smaller one, all right? Big surprise. So the 10.1 is smaller than 26.6. That tells you that the reactant it came from, chlorine, is the limiting reactant. The limiting reactant will make less product. That tells you that the other reactant, aluminum in this case, is the excess reactant. But also really important, the theoretical yield is how much product you can make. And that's the smaller number, 10.1. So I like this method because it does give you really fast the theoretical yield of product. It shows you what the limiting reactant is, and it will tell you what the excess reactant is, which is nice. On the other hand, you can see it takes a little bit more work. Some of the parts repeat, so it's not as bad as it may seem. You can use either way you want to, and there are other ways out there. Just find a way that works. And here's why this is so important. If you quoted to your boss, working as a chemist, that you could make 26.6 grams of Al2Cl6, and at best you could only make 10.1 grams, you'd be fired. You'd get your pink slip and you'd be walking the walk of shame because you didn't think about excess reactant and limiting reactant. You've got to think about it because you can only make in this reaction 10.1 grams, and you may not even make that much because you might lose some, the actual yield versus theoretical yield thing. But anyway, you cannot make 26.6 grams. So this is, again, the power of chemistry, and it's not, rocket science or anything. We just got to put things in order, figure it out. Good to go. So chlorine was the limiting reactant, aluminum was present in excess, but the question is here, how much excess aluminum did we have? All right, if you are using chemicals which are really expensive, for example, gold is actual chemical you can use, and if you have extra gold, your boss might say, why are you putting so much gold in? Maybe there's a reason, maybe there's not. Either way, let's calculate how much excess reactant was left over at the end. This can be useful for not only financial, economic reasons, i.e. you don't have to pay as much, but also for environmental reasons. You don't want to have to clean up the waste. And this way, if you have an excess reactant, would be extra waste. Now, again, there might be chemical reasons why you're adding a little extra. We'll talk about that in Chem 223. But for right now and stuff, yeah, this is a powerful tool in this arsenal of things that a chemist can do. To do this, you have to first of all find out how much aluminum was required based on the limiting reactant. Remember, limiting reactant controls everything. So in this case, chlorine is limiting reactant. We want to find out how much aluminum was actually needed. And then finally, if we know the total aluminum we put in, total aluminum minus the amount used by the limiting reactant will give us the excess. So it's not too bad. We're going to basically do a grams to moles to moles to grams, but this time, grams of chlorine to moles of chlorine, and then moles of chlorine to moles of aluminum needed in the reaction, and we'll turn it into grams and go from there. Back to the numbers we used earlier. We saw that there were 0.20 moles of aluminum and 0.114 moles of chlorine, the limiting reactant, and we found out then that we have to base our calculations on chlorine. So at this step right here, we're taking the grams of chlorine, turning them into moles. We're then going moles of chlorine to moles of aluminum. It's a 2/3 ratio, again because of the balanced reaction, 2/3 to get you there, and then you can multiply by the molar mass of aluminum. And this number is 2.05 grams of aluminum. And that's the grams of aluminum needed to react with 8.10 grams of chlorine. So that number is important. That's the number needed to make the Al2Cl6. However, in this problem, we had a total of 5.40 grams of aluminum, and we only really needed 2.05 grams. So 5.0 minus 2.05, 3.35 grams of aluminum were unused in this reaction. And maybe there's a good reason for it, maybe there's not, but we can calculate it using this thing. So we can at least report to our boss that yes, there was an excess of 3.35 grams aluminum. And then maybe there's a reason for it, maybe there's not, but this allows you at least the tool to start that conversation. Stoichiometry can be used for so many things, and one thing it can be used is to determine a formula. And earlier in this section, we saw an example of propane. It was C3H8 instead of CXHY. But anyway, propane burns in oxygen to make CO2 and water. And this actually is something that happens in all hydrocarbons. A hydrocarbon is just a compound with carbon and hydrogen, and sometimes oxygen. We'll see in the next section. But usually carbon and hydrogen. It burns in O2, and the only products that come out are CO2 and water. So if you have an unknown hydrocarbon with carbon and hydrogen, the moles of carbon and CO2 can be related back to the moles of carbon in the hydrocarbon, the CX, and the moles of water can be related back via moles of hydrogen, that is, can be related back to the moles of hydrogen in the hydrocarbon, the HY. And there's some really cool techniques available in the chemical analytical laboratories to make this kind of thing possible.
A combustion reaction of a compound with oxygen forms water and carbon dioxide. The water, represented as blue speckles, is trapped in one chamber, and the carbon dioxide, represented by white speckles, is trapped in a separate chamber. The mass gain of each chamber can be used to calculate the empirical formula of the compound.
So in this kind of process, you're taking your hydrocarbon and you're basically, like I said, burning it. The O2 comes in, it reacts with your sample, it's super hot, you end up making CO2 and water. But then the stream of CO2 and water, which are both gaseous at this point, are sent through some kind of apparatus. And there's different chemicals we're going to see that absorb water well, and some of them absorb carbon dioxide well. So magnesium perchlorate is the first one. It absorbs water pretty readily. Carbon dioxide can be absorbed by sodium hydroxide as well. There's different chemicals and stuff that we use. I used to use a different CO2 absorber, but that's all right. Either way, if you measure those absorbers before and after, the difference between the masses will be the mass of water or the mass of CO2. And so it's pretty easy to figure out how many grams of CO2 were created and how many grams of CO2 were created in these kind of processes, which is really cool. Let's say that we have just this random hydrocarbon, and a lot of them are kind of oily liquids. That's why it says puddle. But anyway, it's kind of a silly joke. We're going to take that puddle, we're going to burn it in O2. And in this particular example, you end up with 0.379 grams of CO2 and 0.1035 grams of water. Now, you can relate the CO2 back to the carbon in the hydrocarbon. One CO2 comes from one carbon, because there's one carbon in both of them. For water, it's a 2-to-1 ratio. There are two hydrogens in water, so one water came from two hydrogens in the hydrocarbon. And using this kind of process, we're basically going to go grams to moles to moles. We're going to stop at moles, though. We're going to stop with moles of carbon and moles of hydrogen in order to find that formula. And it's pretty cool. Of course, I'm biased. I'm a chemist, but I think it's pretty cool. All of the carbon in carbon dioxide and all of the hydrogen in water in these problems comes from the hydrocarbon, CXHY. So let's find the amount of carbon in the CO2. If you take that grams of CO2, 0.379, and divide by the molar mass, which is about 44 grams per mole, you're going to get 8.61 times 10 to the minus 3 moles carbon dioxide. And I encourage you to try that on your own just to make sure you're good to go. But anyway, one CO2 has one carbon, so 1 to 1. That means there are 8.61 times 10 to the minus 3 moles of carbon that were burned in that sample. 1C comes from 1 CO2. For water, there's that 2-to-1 ratio. So if you take 0.1035 grams of water and divide by the molar mass of water, which is about 18 grams per mole, you're going to get that 5.744 times 10 to the minus 3 moles of water. However, to find moles of water, 1 mole of water has 2 moles of hydrogen. So we'll multiply the moles of water by 2 to get 1.149 times 10 to the minus 2 moles of hydrogen. So remember that 2-to-1 ratio, it's H2O. That's why we're multiplying by 2. We want just the hydrogen from water, just like we wanted just the carbon from carbon dioxide. Now we can find the ratio, and usually it's easier to put the smaller number on the bottom and the larger number on the top, but you could do it the other way. So because the hydrogen was larger, let's put that on the top. We'll put the carbon on the bottom. Now, if you do this ratio, take 1.149 times 10 to the minus 2 and divide by 8.61 times 10 to the minus 3, it comes out to be about 1.33. And that means 1.33 moles of hydrogen per every 1 mole of carbon. Now, you can't keep these things as fractions or decimals like that. However, 0.33 is the same as 1/3. So 1.33 is like 1 1/3. And if you remember from fractions, 1 1/3 is the same as 4/3, 4/3. So 1.33 over 1, you could also say was 4/3 over 1, or just 4/3. There's 4 moles of hydrogen for every 3 moles of carbon. That means the empirical formula, that smallest whole number ratio of atoms, C3H4. So this is a cool way to find the empirical formula, and you don't need really a mass percent as long as you can collect the water and CO2 and back calculate it. Pretty cool little technique. However, there are a lot of hydrocarbons with carbon, hydrogen, and oxygen in them. And an example of this is drinking alcohol, ethanol, which has carbon, hydrogen, and oxygen. If you've ever used acetone to remove like nail polish from nails and stuff, that's a carbon, hydrogen, oxygen compound. And if you have oxygen, there's one little twist we have to do. So in this example, it's going to start out similar to what we did, but there's going to be a small twist. And also in this example, we're going to go not just to the empirical formula, but we're going to go to the molecular formula. Now, this example uses something called caproic acid, and supposedly it has the smell of dirty gym socks. I am fortunate to never have had the opportunity to smell it. I will take people's word for it. But caproic acid, like a lot of acids, has carbon, hydrogen, and oxygen in it. And what we're doing in this problem is you're taking 0.450 grams of caproic acid and you're burning it in O2, and the products, once again, water and CO2. All right. And so that part is kind of like what we did before. However, they're also throwing in here the molar mass of this compound, the whole thing, 116.2 grams per mole. Notice this grams, moles, -1. Moles -1 can also be written as 1 over moles. For example, x to the -1 is 1 over x. So moles -1 is like 1 over moles. So if you see this grams, moles, -1, and you will sometimes, that just means grams per mole. All right, just an alternative way to write molar mass. What is the molecular formula of caproic acid? Now again, caproic acid has carbon, hydrogen, and oxygen in it. So this problem will start off similar to what we did, but it's going to go a little bit different. This compound is different because it is a hydrocarbon with carbon and hydrogen, but it also has oxygen. And this reacts with more oxygen, more O2, to make CO2 and water. So the question is, which oxygen comes just from the acid and what oxygen comes from the O2? And of the CO2 and water oxygen, which of those came from just the caproic acid? So it's the oxygen here which is tricky. But we're going to use law of mass action to figure out how this works. We did not use the grams of the sample in the first example with the carbon and hydrogen thing we looked at, the C3H4 example. But we are going to use this 0.450 gram sample in this problem. Starting it off, we're going to start the same way we did in the last one. We're going to go grams of water and carbon dioxide to moles of water and carbon dioxide, then turn them into moles of hydrogen and moles of carbon, just like we did last time. So here's the example. We'll start with water, 4.418 grams of water. Here's the molar mass of water, turning grams water into moles. 2 hydrogens for every 1 water. This number here, 0.0464, represents the moles of hydrogen, and that's just like what we did earlier. However, this next step is kind of different. I'm going to take that number, the moles of hydrogen, and multiply it by the molar mass of just hydrogen. And to 3 sig figs, that's 1.01 grams. So 0.0464 moles of hydrogen represents 0.0469 grams of hydrogen. And I put both of those numbers in red because we're going to use both of them again here in a little bit. Hint, hint. Now we're going to do the same process, but now with the CO2. We'll start with the 1.023 grams of CO2. We'll turn it into moles using the molar mass. 1 C from 1 CO2, so 0.02324 is the moles of carbon. And again, it's in red. And that's, again, that part is similar to what we did earlier. Earlier, we would have then compared moles of C and moles of H to find a formula, and we would have been done. But the oxygen is there. So, continuing on, I'm going to take that same moles of carbon and turn it into just grams of carbon. So 0.02324 moles of carbon represents 0.2791 grams of carbon. Why did we do that, Dr. Russell? Oh, I'm so glad whoever asked that question. The point, let me get the exact number. There it is. The 0.450 grams caproic acid represents all of the carbon, hydrogen, and oxygen in the sample. And notice that's a gram number. And notice 0.450 grams is less than 0.0469 plus 0.2791. And that's good. The difference is going to be the grams of oxygen in the sample. So again, the sample, 0.450 grams, that's all the carbon, hydrogen, and oxygen in this caproic acid. And we're going to subtract the grams of hydrogen and the grams of carbon to get just the grams of oxygen in the caproic acid. Oh, I get excited by these problems. Oh, nerdy chemist. All right, sorry. Keep on target. Keep on target. Anyway. So 0.450 grams caproic acid is all of the C, H, and O, and specifically all the grams carbon, hydrogen, and oxygen in the complex, in the caproic acid. So if we know that caproic acid has 0.0469 grams of hydrogen and 0.2791 grams of carbon, which we got, by the way, from the CO2 and water converted over, then the difference is going to be grams of oxygen. So you can see what we did here, 0.450 grams, the grams of everything, minus grams of hydrogen, minus grams of carbon, 0.124 grams of oxygen. And that, my friends, is the grams of oxygen in the caproic acid. It has nothing to do with the O2 that was used to burn the sample. And that's the only way that I know of, well, unless you want to get in complicated mass percentages, which I don't recommend, that's the best way to do to figure out the grams of oxygen in this crazy thing. All right, it's the difference of masses. And you can turn the 0.124 grams of oxygen into moles. Mole of oxygen about 16 grams, 0.00775 moles of oxygen. So now we've got moles of oxygen here. We have moles of hydrogen and moles of carbon on the previous slide. If we put this all together, we have a rough formula that looks like that, but it's pretty ugly. So like we did at the end in the last section, we're going to divide all three of those numbers by the smallest number, by 0.00775. That comes out to be 3 carbons, 6 hydrogens, 1 oxygen. So C3H6O, that's the empirical formula of the caproic acid. And again, getting the oxygen was the funky part. We had to subtract the C and H away from the total 0.450 grams to turn in the moles. But that's how this is done. Now, empirical formula, not the final answer. We need to figure out how the empirical formula relates to the molecular formula, and that's where we need the molar mass, which we haven't used yet. So in this problem, if you add up 3 carbons and 6 hydrogens and 1 oxygen, or roughly 3 times 12 plus 6 times 1 plus 16, it comes out to be about 58.1 grams per mole. And you can compare the empirical formula's molar mass, which is this number, to the molar mass of the whole thing, which is the number that's given to you. And you can probably see that 116.2 divided by 58.1, that's a ratio of about 2 to 1. So that means the molecular formula will have 2 empirical formulas in it. C6H12O2 is the molecular formula. So this is a pretty cool thing. You can find formulas based on elemental percentages, and that's what we did at the end of the chapter 2 part 2 stuff. We took like percents of compounds to find empirical formulas and molecular formulas. This is an alternative way. This is based on what's called combustion analysis. Combustion means to burn, and we're burning these crazy things in oxygen to make CO2 and water. You can use those pieces of information then to find a formula too, and that's a pretty powerful technique. Both of these are used in chemistry. It just depends on where you are and what you're doing at the time to know which one is the best answer for you. Okay, that's the end of Chapter 4, Part 1. I really appreciate you spending your time with me. If you wish additional assistance, the study guide, bulleted list of concepts from this particular chapter, I encourage you to just go through it, make sure you're good to go. The concept guide has more worked examples of how these kind of problems work out. And in addition, right after this slide, if you look at the lecture notes, you'll see some important equations I think are important from this section, and also some more end of the chapter problems with answers on the next slide, so you can kind of test yourself, make sure that you're good to go. If you do have any questions, please reach out to me. I'm more than happy to help you anytime. Again, good luck with your studying, and if you have any questions, let me know. Have a great day.